So welcome everyone to the 19th session of Statistical Learning in Practice. Today we'll cover the practical bit of k-nearest neighbor classifiers. And so feel free to ask any questions. So I uploaded the solutions last night, so hopefully you've had a bit of time to look at them.
I was wondering if you could explain in a bit more detail why we sample with replacement when we do bagging.
Okay. So I mean, firstly, you can do both. So it's not like it's a completely hard decision there. Secondly, it has to do with this. So if you've looked at the solutions, then it has to do, so this solution here, it has to do with the intuition that one gets from here. And so, I mean, you're trying to reduce the variance, right? You try to reduce the variance, and then the intuition for reducing the variance is this, is this subsampling that you would have, I think it's around here. I think so. Yeah, so this uniform subsampling without replacement, or with, well, okay, so without replacement, okay, so maybe the question comes a bit from that. I mean, again, it doesn't matter too much. So we'll see the in the example sheet. Actually, we'll do the calculations for without replacement. So it's not really a very hard choice again. I think the only reason here is that Bootstrap is generally, not always, of course not, done with replacement, and so you're sort of subsampling from the distribution and trying to aggregate those classifiers, and that reduces the variance and it doesn't increase the bias a lot. So bagging is actually done in this way for many other classifiers or procedures. So I'm not sure that I have a much better answer to that, to be honest, because you can do without replacement as well, and we'll see how that we can prove some guarantees for that. Well, yeah, some guarantees for that as well.
Okay, thank you.
No problem. And yeah, I ignore whether originally it had any reason to be done that way and not the other way. Yeah, originally as an idea, not, but I can tell you that, there are guarantees and it works, doing it both ways.
In the optimal weighting nearest neighbor function that we use quite late on, when it implements kind of the optimal bag sample amounts and the optimal weights, we didn't cover those, like the form of those in the theory, did we?
Nope. So we didn't, and someone asked, and so thank you for reminding me that. So I said, so someone asked, whether there is a way of getting this optimal estimator. And I said no, because there isn't a way of getting it for, in two respects. So one is for finite samples. So it's not like you can modify your classifier and then suddenly do better. As in you could, but then that would probably be too dependent on the data set that you saw, right? So you could always, you could always change a classifier to give you exactly what you want, right? That's not necessarily better, because the question is whether that generalizes. So changing it to something that will be better in some general way, that's not possible for finite samples and for unknown classification boundaries. Okay, so what is, and this is why I changed the wording a bit, because I didn't like it. It was a bit misleading, the wording here, because it was sort of so this paragraph here, because it was sort of suggesting that the answer to the question I got yesterday was yes, but it's not, because so we see actually here an example in which the bagged classifier outperforms the optimal weighted nearest neighbor classifier. But that's because the optimal weighted nearest neighbor classifier is only so asymptotically, just in the same way that the bagged classifier is also optimal asymptotically. And also importantly, it is optimal under some regularity assumptions on the classification boundaries. And you cannot check these. So in some problems that are not, nearest neighbors for classifying, one can tweak the estimators in such a way that even when they don't know the regularity of the of the quantity that you're trying to estimate, so I'm thinking a bit more of density estimation, then you can modify them in such a way that they will adapt to the unknown regularity, and they will even do optimally for every single regularity, without knowing it. Okay, but that's not the case for this optimally weighted nearest neighbor. It is optimal given the regularity that is assumed, to construct it. So it is a bit misleading to call it optimal, but that's how it was introduced in the literature. And it's the same idea with this resampling fraction, optimal resampling fraction. So it's only so under some regularity assumptions. Okay. What else do I want to say about this? Yeah. So this optimally weighted nearest neighbor classifier is attained via an expansion. Okay, so you just imagine some sort of Taylor expansion and then keeping the first term, the first order term. And so, of course, as with the asymptotics, what happens is that you kill the second, third, and so on terms. But when you're not under asymptotics, the first term is indeed the dominant one, but it's not the only one there. So that's why you won't be optimal for finite samples necessarily.
Could I clarify that means you've got a constant set of weights for a given D, or what is kept constant here?
What is kept constant?
So as in what are the optimal weights a function of? So that's what I should say.
Oh, I see. Oh, for that you need to go to one of the references I gave in theory. So it's not constant, no.
Okay.
So, okay, and this relates to another question I got yesterday, which I'm not sure I partly misunderstood, but because I was just thinking about it again last night in terms of whether I misunderstood that. But so what these weighted nearest neighbors will do is to weight, the weights will not be equal for every neighbor. And so it may be that you give more weight to the closest neighbor, but how you do that and why you do that depends on the regularity of your function, of your classification boundaries. Okay. So firstly, just to answer your question, Michael, just go to the reference. So Samworth 2012. You will see the expression there. Second, regarding the question I got asked, what I understood is whether you could make the weights depend on the covariates in some sense. That's what I understood. And that's something that is not something I've seen, but maybe that's not what was being asked. So maybe what was being asked is simply, I don't know, something else. I don't know if I misunderstood that question or not. But certainly you can make them of different weights, and that will make you adapt to different regularities. Okay, but because you don't know the regularity in advance, then it's not always the case that the optimally weighted nearest neighbor is actually optimal.
Thank you very much.
No problem.
Just quickly, all these asymptotics are like n going to infinity, right?
Most of them, yes.
Okay, thanks.
Yes, I think it was you who asked about that, right? About the weights coming down.
Yes, I think so.
I
mentioned some sort of kernel distance thingy.
Oh yeah. So what was? Do you remember your question? What it was exactly, precisely?
Just that, would it be reasonable to try something like that? And indeed, do other people do some people use it in practice?
Something like, can you specify what?
Something like weighting the average of the classification by making kind of nearer points have more weighting to your kind of average of the k nearest neighbors.
Okay, but you weren't thinking of introducing the covariates in the weights or something like this? Somehow I understood that, and that I found strange.
I'm not sure, maybe. I mean, presumably the distance between the points is the covariates.
Yeah, totally. Yeah.
So,
this is why you wouldn't. Yeah. I mean, yeah. No, I was thinking you were thinking of doing some sort of, like a linear predictor, using it in an exponential or something like this. I probably misunderstood what you were saying.
It wasn't very well formed, so
That's okay.
Probably open to interpretation.
Right.
Just to clarify one thing, in the theorem at the end of the lecture yesterday, we have that the risk of the infinite bagged one is less than or equal to the optimal K star.
Yep.
So just, I guess, two things. First of all, so this is like for large enough n, eventually this holds.
Yeah. Although, yes, that's that kind of result. Yes. Although I would say that you can definitely, if I were you and I was doing this in practice, then I would definitely use the backed one rather than the other one, because the other one, firstly, is not a weighted, it's not, a classifier with different weights, and generally that performs worse. And secondly, it's based on this guy, which is also asymptotic. So
yeah, and just kind of to clarify, asymptotically, therefore, it not only does the bag infinite one beat K star, it therefore also beats all other K because the K star is optimal.
Yeah, exactly. Yeah.
Yeah.
Oh, and also I got a question about the positivity of the weights, and that I made a mistake by saying that they had to be positive, so they can be negative. There's nothing about that here in practical, but there's nothing. I mean, it's just very unnatural, but there is nothing against you taking them negative, the weights. So there is more details of that in this reference of Samworth 2012.
This might have been asked before because I didn't go to the office hour, but if the proof of the existence of the optimally weighted classifier is non-constructive, then what's the OWNN function actually doing?
No, because this one, no. So this one is constructive. The optimal, so the one that you get here is certainly constructive, because you do it through this expansion that I was saying of just taking the first order term in some sort of Taylor expansion, and that doesn't guarantee that this guy is optimal for finite samples or without the regularity assumptions, but it does in terms of asymptotics because the rest of the terms will die out basically as n goes to infinity.
Okay, thanks.
So you can see it in Samworth 2012 the exact weights that you get for it.
So for the optimal weights, with this like n to the minus d over d plus 4 over d plus 4 thing, when I've seen similar results like this before, it's often some constant times n to the something, and so you know sort of like the asymptotic decay of the optimal parameter, but you might not necessarily know the asymptotic like actual value because you don't know the constant. Is this a case where you actually do know the constant, or is there something else going on here?
So I forget exactly the constant, exactly how it is, its form, but I would
just because in almost all of the examples I've seen before of stuff that looks like that, the constant depends on a lot of things you don't know.
Exactly. So that's generally the case in non-parametrics, in non-parametric statistics, because what happens is that the constant will depend on this regularity assumption, and the regularity assumptions are not known. But there are ways to tweak estimators so that they adapt to these unknown constants and even rates. Yeah, because it's also the case that the rates depend on the regularity. Okay.
Yes.
But so this constant, okay. So don't quote me on this, but even though I'm recording myself, but take a look at Sandbor's 2012. I would swear that there is a constant there that is given explicitly, but it is also very likely that it will depend on the regularity. Yes.
So I'm just wondering if there's any more to be said about what this function is actually doing. If the so it's a sort of optimally weighted, but presumably there's more to knowing what the optimal weights are going on.
Yeah. So you're talking about this function, right? The OWNN.
Yeah, that one.
No. So I mean, this is only computing this first order term in the expansion, together with this guy. Oh, so you're saying how?
So what I'm saying that so that I know the optimal weights will sort of have that behavior, but that seems to like it might depend on a constant. And is it sort of approximating this constant or?
Right. So actually, I don't know whether it is approximating it, but my guess is that it is not, and that it is simply taking some value of the regularity.
Okay, and that so it's like assuming a certain constant, say.
Yes, because I think
because it will depend on regularity.
Exactly.
Okay, no, that makes sense.
Because in Sandbor's 2012 there is a very precise assumption about the regularity, and so in some sense you're fixing the regularity. So I would guess that is what's going on here.
Okay, thanks.
No problem.
I can't remember if you said anything about this before, but we seem to be comparing like k nearest neighbors with maybe a sort of clever choice of k and even weighted nearest neighbors with this bootstrap resampling like one nearest neighbors. Is there anything to be said about bootstrapping k nearest neighbors? Because it seems to be that we have like k or one with bootstrapping. Do we ever think about k with bootstrapping?
Okay, so the answer is I don't know, but I can also tell you that the reason to bootstrap, so the reason to do bagging is that you wish to reduce the variance without changing the bias a lot. And so that makes sense precisely for the one that has the best bias and the worst variance.
Oh, okay, right. I
One
see.
neighbor.
Yeah, that makes sense.
Yeah.
Okay, no, thanks. Yeah.
Sure. So yeah, maybe you can do it with a 2NN classifier, but doing it with any NN, I think you got the point that it may not be necessarily useful.
Could you maybe give some intuition why in the MNIST part, rotating the data improves our estimations?
Yeah. I mean, it's just because some digits, some instances of the digits, so some data points, when you're writing a number, it may be that it's not aligned exactly with the paper, right? And so if you train the algorithm with rotations, then it will be able to pick up slight variations that you're writing, right? It's no more than that. I mean, it's just that if you augment it with different things that could be happening, then you will adapt better to whatever is happening. So there isn't much more to it than that.
Okay, sure.
So this was, what was this? So over a decade ago, it was actually quite a hard problem to say that you're classifying something and okay, so let's focus on numbers, and you rotated it completely, sort of 180 degrees. Then it was very hard to build algorithms that were efficient that would classify that as a number 2, say, if you rotated 180 degrees. So a cheap way of doing it is just this, is giving it. So embedding invariance was not easy or cheap unless you did it this way, sort of several years ago when we didn't know, when we didn't have the algorithms that we have now.
Okay, thanks.
No problem.
Yeah, just to follow up on that, just to know if the KNN is really good because we have 5%. What's the best error that we can get today?
I don't know it by heart, but certainly it's much better than this. So I'm sure you can, if you Google it, you will get it. But yes, it's true. I mean, many competitions are based on this MNIST data, and and they've been, they've been getting better and better every year. And I don't know, I wouldn't be able to give you an exact percentage that there is now, but certainly.
Just Googled it, 99.5-ish.
Right, yeah.
Okay, quite good, yeah.
You mentioned a kind of modern methods to preserve invariance when you said that, just like a minute ago. What sort of ideas are behind these?
So in many occasions, it's much more about finding a latent space that explains things. I mean, there are, of course, there are many ways of trying to get these invariances. So for instance, you could have, as I mentioned briefly in the theory, you could have taken, rather than the L2 norm, could have taken a different norm that preserves invariances. So that's one way. But then other ways are, for instance, now we have this, and this is quite recent, is, these latent spaces that don't really care about the, how rotated the image is. So they really pick up something that is more profound than that.
That sounds pretty cool.
Yeah, and I mean, you have yeah, I mean, so the, so you must have heard, a couple of years ago that the self-driving cars, they stopped the experiments because they had a couple of crashes that they couldn't explain, and then they went back, to the lab, so to say, and sort of started thinking why this is, and that actually gave rise to an explosion of methods on robustness, because it was being understood that neural networks, which are essentially the workforce of these methodologies, they were not very robust to very small changes, so very small perturbations. They could be, deceived by tiny, as small as you like, perturbations. So one could show that mathematically, and this gave rise to a lot of robustness methodologies that are robust to these little changes, and they also go via these latent spaces. And so the massive advances that we've seen now in the last couple of years have a lot to do with these latent spaces and robustness and so on. Okay, so I'll give you 3 more minutes. Maybe for once we can have a session that is less than 50 minutes. I'm sure everyone will appreciate it. Yep. Is there a question?
Yeah, when I was running the OWNN, even keeping the sample constant, I got that ONN sometimes gave different results. I might have mucked up somewhere.
Mm-hmm.
But isn't that surprising that there's some randomness, even if you're just running the last line of code repeated times?
So you mean running this again and again?
Yeah, but yeah, not running the testing multiple times, because that would give a randomness.
Yeah, that is a bit strange. I just think. Yeah, that's a bit strange, actually. You sure you're not? Yeah, you're not changing the test, of course.
I don't think so, but it's possible. Has anyone else tried it?
Yeah, just running it twice on mine, it does change slightly.
Okay, so Yeah, that is a bit strange.
When I looked in the documentation for the KNN one, it does use cross-validation to pick the best K.
Right.
But for the other two, it doesn't say anything about what it does. So I'd assume it wasn't.
So you said for the optimal K, it does cross-validation?
Yeah, because it gives 3 outputs, but for the other two, it doesn't say what it does, but it still appears to have some randomness.
Okay, so then that answers the question I got on the constant. Firstly, that no, so then no constant is computed here. So yeah, it's done via cross-validation, and that also explains why it is random, because the expression for optimally weighted nearest neighbor depends on this K star, and so the K star is changing with cross-validation then.
Yeah, thanks. Makes sense.
Yeah. Okay. Yeah, sorry then. So I was assuming the constant was being computed. So actually what is being done is a bit more sensible than computing that constant, and probably also explains why the the bagged classifier is does it no, it doesn't explain that. Okay, sorry. Yes, it just answers the question about the constant. Yes. Okay, any more questions? I'll give you 2 more minutes, and then eventually we'll make it a 50-minute session.
I'd just like to kind of clarify, when reading the Samworth paper, it looks like the WINs weight the ith nearest neighbor to the point we're dealing with.
Yeah.
Great.
So sorry. So what's the point?
So the W's kind of vary with the points, but the WNIs are fixed. So the specific weight values are fixed kind of in advance, but depending on which point we are depends on which weights correspond to which nearby data points.
Right. Yes. Okay. So that's a bit akin to what you were saying.
So there's a little bit of kind of distance dependency, but only in terms of the ordering of the distances rather than their actual values.
Right. Exactly. Yeah. So, I mean, this is why I said that I think I misunderstood the question, because I thought you were thinking of doing some sort of regression on the weights as well at the same time, something of this kind. So using some linear predictor.
Maybe that's worth some research. Probably not.
What else was I going to say? Yes. Okay. And so how it changes with X is implicitly assuming some assumptions, right, on the regularity of the classification boundaries. Because of course, depending on how the boundaries are, you would take a different behavior than other, right? So all these are just based on some assumptions that in practice you cannot check in advance. And this is, the only criticism, if any, but I mean, there's still great great advances. And I would swear, I mean, so there are now adaptive. So adaptive is this that I was talking about, of adapting to this unknown regularity, and there are some adaptive procedures now on k-nearest neighbors. So there is recent work by Samuth as well on that, and also applied to different problems, not classification.